carbohydrates part. In carbohydrates, generally carbohydrates are considered hydrates of hydrates of carbon. With the general formula CxH2O taken 5 times. CxH2O taken 5 times. The ratio to the hydrogen to oxygen will be 2:1. For example, if you take glucose hydrogen oxygen ratio will be Cx, and it is following this formula. Therefore, it is a carbohydrate. Acetic acid is not a carbohydrate, but it is following the same formula. Rhamnose is a carbohydrate, but hydrogen to oxygen ratio is not following this formula. Therefore, the carbohydrates redefined. These are the polyhydroxy polyhydroxy aldehydes or ketones are the compounds which on hydrolysis gives these compounds we are calling carbohydrates. Carbohydrates also called saccharides because generally they are sweet in taste, hence we are calling sugars. So the final definition is polyhydroxyaldehydes or ketones are the compounds which on hydrolysis gives these compounds we are calling carbohydrates. Now let us discuss one by one based on hydrolysis. If you see carefully, carbohydrates we classified into polysaccharides, we classified into oligosaccharides, we classified into monosaccharides. Polysaccharides and hydrolysis giving oligosaccharides, oligosaccharides and hydrolysis giving monosaccharides. So monosaccharides are the simple carbohydrates. They cannot be further hydrolyzed to give simple unit. So these are the simple carbohydrates. We are calling monosaccharides. If aldehyde is functional group, we are calling aldose. If ketone is functional group, we are calling ketose. The simple carbohydrate contain generally 3 to 8 carbon atoms. So if 3 carbons are there, we are calling aldotriose. If ketone is there, means we are calling ketotriose. In aldotriose, the best example will be glyceraldehyde. So in glyceraldehyde, we have chiral center. So because of chiral center, it is optically active. It is forming D-glyceraldehyde and L-glyceraldehyde. Both are examples for enantiomers. Important question. So next one, let us talk about. So these, if 4 carbons are there, we are calling aldotetrose. If you see carefully, aldotetrose, CHO and CH2OH. So we have OH group, we have OH group right side. Here we have hydrogen, here we have hydrogen. So D-erythrose and L-erythrose, both are example for enantiomers. This question is asked in NEET 2016. Important. Erythrose means similar groups present same side. Triose means similar groups present opposite side, you see. Trio, opposite side. Erythro, same side. NEET 2016 question. Important. So next one I am taking aldopentose, that is D-ribose, as well as I'm taking D-arabinose. So in the case of D-ribose, all the OH groups are same side, whereas in arabinose, at first carbon you see OH group is left hand side. So finally, we are going to the next one, that is aldohexose. Aldohexose is nothing but glucose. We have two structures. First one is D-glucose, second one is L-glucose. How to write the structure of glucose is very, very important. I'm giving one shortcut. If you know this shortcut, you can write the structure easily. So this will be first carbon, second carbon, third carbon, fourth carbon, fifth carbon, sixth carbon. So what is the super trick? What to remember? You have to remember 3L. At third carbon, we have L. L means left hand side we have OH group. This you have to remember. So D-glucose and L-glucose exactly opposite Bangaram, opposite side we have, the opposite uh, arrangement is there. In D-glucose, number of chiral carbons will be four we have. You can check this. Here, this will be one, second one, third one, and fourth one. Number of chiral carbons will be four, and primary alcoholic groups we have only one, and secondary alcoholic groups we have total four. And IUPAC name of D-glucose is important. 2R, 3S. Just now I told you 3L, 3S, 4R, 5R, 2 comma 3 comma 4 comma 5 comma 6 pentahydroxy 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 hexanol aldehyde is a functional group, whereas L-glucose is also important. L-glucose will be 2S, 3R, 4S, 5S, pentahydroxy 2 3 4 5 6 pentahydroxy hexanol. IUPAC name is important. So D-glucose and L-glucose both are differ in their configuration. We are calling enantiomers. Non-superimposable mirror images we are calling enantiomers. So D-glucose, L-glucose, chiral carbons important 4. IUPAC name is important. Primary alcoholic groups will be 1 and secondary alcoholic group will be 2. Very, very important. So next, let us focus. Next one, I am taking what are epimers. So epimers is nothing but a pair of diastereomers which differ in their configuration other than C1 carbon. A pair of carbohydrates or epimers are diastereomers which differ in their configuration other than C1 carbon. You see carefully. The best example, D-glucose and D-mannose are C2 epimers. D-glucose and D-mannose are C2 epimers. So here the difference will be only at C2 carbon you see. In the case of glucose, OH group is right hand side. In the case of mannose, OH group is at left hand side. Similarly, D-glucose and D-galactose, very, very important. The super trick is you have to remember, in the case of glucose, remember 3L. In the case of galactose, 3, comma 4L. There is a difference, the difference between glucose and galactose. Difference between glucose and galactose is at fourth carbon, hence glucose and galactose we are calling epimers, C4 epimers. All epimers are diastereomers. All epimers are diastereomers. Important. So next one is very, very important. D-erythrose and D-threose. Just now we discussed erythrose means similar groups will be same side. Threose will be similar groups will be opposite side. Both are C2 epimers. They differ in their configuration C2 carbon. Important. And cyclic structure of glucose. One more important point, what are anomers? Anomers is nothing but a pair of carbohydrates which differ in their configuration at C1 carbon. If they differ in their configuration at C1 carbon, you see this is first carbon, OH group is right hand side. If OH group is right hand side, we are calling alpha D glucose. If it is the left hand side, we are calling beta D glucose. Right hand side, alpha D glucose. Left hand side, beta D glucose. Alpha D glucose melting point is 419 Kelvin and the melting point of beta glucose is 423 Kelvin. So a pair of carbohydrates which differ in their configuration at C1 carbon we are calling anomers. Other than C1 carbon we are calling epimers. So how to write the cyclic structure of glucose? Very, very important one. So carefully note it. So we are writing pyranose structure to the glucose. Pyranose structure to the glucose. So pyranose structure to the glucose we are writing. So pyranose structure to the glucose we are writing. See carefully. So first carbon, second carbon, third carbon, fourth carbon, fifth carbon. So the groups which are present right side, the groups which are present left side. Right side groups always we write below. This structure we are calling Howrah structure. Left side groups always we are writing above. Right side below, left side above. First I am writing this. The first carbon OH group is the downside. Next OH group is the downside. Third carbon OH group is left side I am writing. This is already I told you 3L and OH group will come here. The finally H CH2OH. So if it is downside, H will be coming above side, the upside. So H, H. So this is the structure of alpha D glucose. Howrah structure we're calling. So similarly, let me explain the beta structure. Carefully you see. So this is going to be beta structure. So first carbon we have, second carbon we have, third carbon 3L. 3L. Beta means OH group will come upside. So here we have H, here we have OH, here we have H, here we have OH. The last one is HCH2OH. So this is very, very important. Difference between alpha D glucose and beta D glucose. Important. They differ in their configuration only at C1 carbon, you see. C1 carbon OH group is the downside, right side, alpha, left side, beta. Very, very important. So next, we are talking about this one. Already we discussed pyranose structure. In pyranose structures, we have five carbons plus one oxygen is there. Five carbon and one oxygen is there. Next one is fructose, levulose, and it is fruit sugar. It is present in honey. Sweetest sugar is fructose. It is a ketohexose. Ketohexose. And here you see C double bond O group is present. Ketone group is present. It's second carbon. Carefully note. So the super trick here also I'm explaining 3L, 3L, first carbon, second carbon, third, fourth, fifth, sixth, third carbon L, 3L, 3L is the super trick to remember the structure 3L. So this is the structure of fructose and already I discussed alpha and beta. OH group is right hand side alpha, OH group is left hand side beta. Anomeric carbon in glucose is C1 and anomeric carbon in fructose is C2. Very, very important. Cyclic structure. This we are calling pyranose structure. OH group is right hand side, we are calling alpha. Left hand side, we are calling beta. Pyranose means we have four carbons plus one oxygen we have. Four carbons plus one oxygen we have. So what do you mean by reducing sugars? Sugars which reduces tolerance and failing reagent. Sugars which reduces tolerance and failing reagent, we are calling reducing sugars. Reducing sugars reduces tolerance and failing reagent due to presence of maybe free aldehyde group or ketone group or due to presence of amiacetal structure. Important. If carbon contain alkoxy group and hydroxy group, so this situation we're calling amiacetal structure. So they're acting like reducing sugars. Reducing sugars shows a phenomena of mutarotation and also they react with phenylhydrazine and forming oxazone. Forming oxazone. All monosaccharides, whether aldoses or ketoses, are best example for reducing sugars. Fructose is a reducing sugar. Fructose is a reducing sugar. Why? Even though it is ketohexose, it is a reducing sugar. Why? Fructose reduces tolerance reagent due to enolization of fructose followed by conversion to aldehyde by base. So this is very, very important. So this is the structure of fructose. What is happening? Double bond is going here, hydrogen is coming here. As a result, we are getting enolic form, and which is finally converted into glucose, and finally we are getting mannose. Ultimately, what happened? Sorry. So enolization, because of enolization, the fructose contained glucose, fructose, and mannose. So that rearrangement we are calling low berry D brain monocyclic instant rearrangement we are calling. So because of this, it is acting like a reducing sugar. Next, let us discuss about the chemical reactions of glucose. Glucose formula will be C6H12O6. And when you treat glucose with tolerance reagent, failing reagent, bromine water, HNO3. Tolerance reagent, failing reagent, bromine water, we are getting gluconic acid, which indicates presence of aldehyde as a functional group. Only aldehyde is oxidized, you see. Only aldehyde functional group is oxidized in all the cases. With tolerance reagent, with failing reagent, with bromine water, you're getting gluconic acid. But HNO3 is a strong oxidizing agent. We're getting saccharic acid or glucaric acid. Saccharic acid or glucaric acid we're getting. This oxidizes aldehyde into carboxylic acid as well as primary alcohol into carboxylic acid. This is very, very. When you treat glucose with HI, we are getting N-hexane, which indicates all the carbons, not only glucose, fructose also reacting and giving N-hexane, all the carbons present in straight chain. And when you treat glucose with NH2OH, we are getting oxide, which indicates with the HCl also we are getting cyanohydrine, which indicates the glucose may contain carbonyl group as a functional group. Carbonyl group as a functional group. So when you treat glucose with acetic anhydride or acetyl chloride, we are getting penta-acetyl derivative. Penta-acetyl derivative we are getting, which is indicates presence of 5 OH groups. Presence of 5 OH groups. Important. So next one, very, very important. The open structure of glucose does not react with Schiff's test, does not react with sodium bisulfite, does not react with 2,4-DNP, and pentaacetate of glucose does not react with hydroxylamine. So this is very, very important. You need to remember. No Schiff's test, no sodium bisulfite, no 2,4-DNP, and no pentaacetate derivative does not react with hydroxylamine. And glucose, already we discussed when glucose react with 3 moles of phenylhydrazine, we are getting osazone. Oligosaccharides. If monosaccharides are say, we are calling best example will be maltose. Maltose is a combination of glucose. If monosaccharides are different, example sucrose, lactose, glucose, and fructose. So the first one I'm talking about sucrose. Sucrose is a disaccharide, which on hydrolysis we are getting alpha D glucose and beta D fructose. NEET 2020 question. Alpha D glucose and beta D fructose. And by eliminating, you see here, this is C2 carbon of the fructose. This is alpha D glucose. This is beta D fructose. C1 carbon of the alpha D glucose and C2 carbon of the beta D fructose binding by eliminating water, loss of water by oxide linkage. You say this is oxide linkage as a result. That linkage we are calling glycosidic linkage. And there is no free aldehyde and ketone group. Therefore, it is a non-reducing sugar. So it is a non-reducing sugar. And it is a invert sugar, invert sugar. Maltose. Maltose is a on hydrolysis giving two alpha D glucose units. Ames 2011 and 2014 question. Both are alpha D glucose units bonded by using C1 carbon and C4 carbon, C1 carbon and C4 carbon. Lactose, C1 carbon of the beta D galactose and beta D glucose. So as a result, we are getting a glycosidic linkage and it is a reducing sugar. What is mutarotation? Alpha and beta D glucose have different specific rotation. Alpha D glucose is 112, whereas beta D glucose is 18.7. What is happening? Alpha try to convert into beta and beta try to convert into alpha by getting equilibrium mixture 52.5. Therefore, the change in specific rotation at the time we are calling mutarotation. And all reducing sugars shows mutarotation. There is a question in AFMT 2010. Which of the following does not exhibit the phenomenon of mutarotation? Only reducing sugars shows the phenomenon of mutarotation. So therefore, sucrose is a non-reducing sugar, does not show mutarotation. Polysaccharides. Important question, NEET 2018 question. Starch is a polymer of alpha D glucose. It contains amylose and amylopectin. Amylose is water soluble and gives blue color with iodine. It contains 50 to 20% of starch. Long linear polymers. It contains 200 to 1000 alpha D glucose units by C1 C4 glycosidic linkage. Amylopectin is water insoluble. 80 to 85% of starch. Branched chain polymer of D glucose. C1 C4 linkage we have linear and branched will be C1 C6 linkage we have. And this question is asked in NEET 2018. So amylose alpha linkage. So in the case of amylopectin, we have branches C1 and C6. So see the question, NEET 2018, the difference between amylose and amylopectin. Amylopectin 1, 4 and 1, 6 linkages are there, whereas amylose is made up of with 1, 4 linkage. Next one is cellulose. Cellulose is a polymer of beta D glucose and C1, C4 glycosidic linkages we have. Most abundant organic substance in plants. Glycogen is animal starch which contain alpha D glucose and structure is similar to amylopectin, but more branches are there in the case of glycogen, present in liver, muscle, and brain, etc. So this is about carbohydrates part. Please like and subscribe. The very clear detailed biomolecules video is already is there. You can go through it. Thank you.